introducing our last speaker of the first part of the semester. Let me remind you of some events after the break. So it's a week-long break. Our first talk on right after the break will be given by Alia Rumana, who is our postdoctoral fellow at the center, and she will be talking about DCNN-based models in visual neuroscience. So a talk in the philosophy of neuroscience. There is no talk on Friday, the week after the break, but there is a conference on Saturday and Sunday on pragmatism and scientific measurement with Jaeck Chang, Nancy Cartwright, Eran Tal joining us. If you want to come to this conference, please go online and register for the conference so that we can have a head count. On Monday, March 17, we have an impromptu workshop on emergence here at the center in this room. It starts at 9:30 and will be over around 5 or something like that. The program is not yet online, but we're creating the web page for the program. And our fellow Andrea, who is at the center, is organizing this workshop. I think, David, you're talking at the workshop, that's right? Yeah, and I don't quite remember who else is talking at the workshop. Bob is, yeah, so David, Bob, Andrea, and a few other people are joining this workshop. Please join us for that meeting. Today, it's my great pleasure to introduce Frederic Jaeck, who is a fellow at the center this semester. He's a philosopher of mathematics working at the CNRS, Université de Paris, Sphere Laboratory, and at the Université de Aix-et-Marseille in the south of France. Beautiful places. If you haven't been to Aix, I highly recommend. Aix is a lovely, lovely, lovely place. He is a philosopher of mathematics. He's got a PhD both in fundamental mathematics and in history and philosophy of mathematics. He has published widely in the history and philosophy of mathematics on leading mathematicians such as Adama, for example, who work a lot actually on mathematical thinking, Volterra, Banach, Lotman as well. And I should mention in 2021, he was one of the editors of the lecture Protodinkian.
Yes, yes.
About right, so right.
Okay,
this is the right way to pronounce it. He's a founding member of the and editor of the Annals of Mathematics and Philosophy. In fact, you can see outside. I wanted to take the book with me, but I just forgot. Outside at the entrance, there's a few copies of one of the issue of the journal. Feel free, I suppose, right?
There are 2 issues, and you can take them.
Exactly. So feel free to take one if you're interested, and to have a look a bit at the journal. That's a place. If you do philosophy of mathematics, you might be interested in publishing and submitting paper too. So so we are happy to advertise on Zoom and in person here this relatively new journal that Frederic is actually editing. So today Frederic is going to be talking about what is called thinking in mathematics. Today, floor is yours.
Okay, so first I want to thank Eduard for this generous presentation, of course, and even more importantly, for keeping alive a tradition that is absolutely essential to philosophy, a blend of freedom and encounters that makes these lunchtime talks so special. And thank you all for being here, of course. It's really nice to have you here. So my title quite faithfully reflects what I've been working on for many years now. And at first glance, it might seem a bit bold to revisit the question of thinking, since it has a long, complex history. It is, of course, a nod to Heidegger's what is called thinking, was Eist Denken, the lecture course he gave in Freiburg in the 1950s. And I believe that many philosophers here would say they are also working on the same question from their own perspective, since it's quite a central question in philosophy. So there won't be anything new here, except I think a real shift of perspective, one that I believe that can help clarify or even rethink some long-standing questions in the philosophy of mathematics. Before I begin, I would like to take a couple of minutes to explain what for me justifies revisiting this question of thinking in mathematics, especially in our time. So I would like to bring forward two types of ideas. One on the side of mathematics and one on the side of philosophy. And then we say a word of this separation between the two. So first, maybe on the mathematical side, I think that there are new things happening. And I think this is the role of philosophy grasp changes in mathematics today. So the two new features I want to mention are first, what I will call maybe cross-domain strategies. To put it simply, mathematicians tend to take strategies from one domain, including structural approaches, and only partially adapt them to work in another domain. It's not a faithful transcription from one domain to another domain, but rather a partial adaptation of ideas from one domain to a new context. Both domains, in fact, can be affected by this transgression of the original boundaries of the strategy, or what I will call a bit later, the legal domain of some rules. So maybe let me quote Timothy Gowers when he took his position at the Collège de France a couple of years ago, where he gives a lecture on combinatorics. So this is a quote. A second reason for the higher reputation of combinatorics enjoys today is that some of its aspects, including those that interest me most, have turned out to be surprising links with more mainstream mathematics. These links exist in both directions. Tools from other fields have been used to solve combinatorial problems, and tools from combinatorics have been used to solve problems in other fields. And this is dedicated to a large audience, but even in very specialized groups, Gowers says a bit more. There are in fact three non-completely distinct ways in which Ramsey theory, you don't have to know what Ramsey theory is exactly here, is useful in the study of Banach spaces, no Banach spaces, theories, different theories. It's just because I said what it was about just before. So there is Ramsey theory and Banach space theory. The first is most obvious indirect application of existing results from Ramsey theory. The second is the discovery of new results in Ramsey theory obtained with the specific aim of applying them to problems in Banach space theory. And the third way is the proof of pure Banach space results that are Ramsey theoretic in character and inspired in the method of Ramsey theory. So this kind of thing is, I think, quite new in mathematics and not worked in the philosophy of mathematics. So you see here the subtle influence of the cross-domain strategies acting partially in the two domains. The second important shift is maybe the use of artificial intelligence here. I think we only see the early tremors of this impact, but it's already being integrated into many mathematicians' daily work, not only for checking proofs, verifying conjectures, and performing computations, but also for generating new ideas, in fact. It may perhaps become a new ingredient in the way mathematicians think. Maybe just a remark here. The main difference I see between what machine can do and what mathematicians can do is this. I think machine can play a game with given rules and become very efficient at it. See how it works with chess or Go games or that kind of thing. But I think mathematics are not merely a game in which we seek to excel. Some of us try to excel. It's good to excel. Okay? But what mathematicians do, in fact, at their best, I think, is invent games that give meaning to our human condition. I won't dwell on that too much here because it will be out of the scope of a single talk, but this is important to me. Now, on the philosophical side, I will pick two words, only two words, that in a way shape many contemporary debates in the philosophy of mathematics. The first is structure, and the second one will be object. Of course, the two are intimately linked, and I could spend quite a long time bringing on the scene all the philosophical stances that try their best to deal with those two important notions. To avoid this, I will only say a few words here and say my concern with those two notions as they are treated by philosophers. First, structure is a word that both mathematicians and philosophers use. The main problem to me is that philosophers very often use it as mathematicians do, but within a form of thinking that is not mathematical. Simply put, they import into philosophy a concept that belongs to mathematics. But to me, there should be a clear separation and even an autonomy, total autonomy of philosophy, its concepts and its questions. John Burgess has done tremendous work on structures in mathematics. Analyzing Bourbak's use of structures, he states in his 2015 Rigor and Structure, the word structure is a common label for what I have heretofore rather accordingly been calling space or number systems or whatever, this is whatever, a label for the genus of which group, ordered sets, topological space, and more are species. So he opens up the concept of structure in the context of mathematical practice, but you will see how I propose to reconsider the term from a philosophical perspective here. Concerning objects, I would like to quote Elaine Landry's, who was developed, what I believe to be one of the most advanced views in the philosophy of mathematics, and on how we might grasp, in fact, the notion of object and structure and much more. Her stance is known as ifism, and I put her here. I use my reading of Plato to develop what I call as-ifism, the view that in mathematics we treat our hypotheses as if there were first principles, and we do this with the purpose of solving mathematical problems. I then extend this view to modern mathematics, wherein the method of mathematics becomes more the axiomatic method, noting that this engenders a shift from as-if hypotheses to as-if axioms, etc., etc. You see here that what is treated as if there were hypotheses, then axioms, perhaps even systems that have a structure and so on. This is what is problematic, I think. It is an open approach, and I feel quite close to it, as it seems to lead towards what I would call a general theory of thought. But my main concern here is that these hypotheses, or once again, these structures, which remain confined to what mathematicians say in their work, this is in fact problematic. Yes, I believe they mean much more than what is meant here. They belong to a broader philosophical picture. So what? How can we start again on the philosophical side without embarking too much from the mathematical concepts? I mean concepts that as they are used in the mathematical work or practice. I start with something we can all grasp. That is what we express when we say, I am doing mathematics, or I'll go and do my math now, or anything similar you might say when you are a kid at school, or later at the university, or even as a professional mathematician. You do mathematics. So to start with something as close as possible to this common idea, I will take the verb to think, or its form thinking, if you want. It's a simple verb. Think it as just a verb, as opposed to I think, the famous cogito, where you have the subject included in the form. I explain this now. There will be some maths, but strictly the minimum, I promise. And but some maths because it's a philosophy of mathematics. So, here is the plan of the talk, in fact. There are many points, so I have an eye on the watch. I stop when it's over and will be enough. So the first point is two modes of thinking. This is the main machinery here. Then a purposeless machine. I want to give an abstract, very abstract tool to think about thinking. So it will be a purposeless machine. One small example, and from this I derive different things if you look at the titles, you always see somewhere the two modes of thinking, okay? Objects and something, well, we'll see that. And if I have time, I talk about this very interesting thing. I have to talk of those two modes of thinking, but they are in reciprocal contamination when we think. So two modes of thinking. My philosophical claim is that there are two modes of thinking in mathematics, two ways of exerting our power of thinking, which is not, which cannot be fully understood without considering their interrelation, and even what I will call the cross-contamination of these two modes of thinking. I use the word mode, which I think is more commonly used in French than in English, because it conveys something a bit more specific than simply ways of thinking. I don't want to dwell on this right now, but you might think of it like modes in music. Not merely a scale or sequence of degrees, but something more subtle that makes something recognizable, that allows us to see a family resemblance in music, in fact. It's indeed a link to a choice of notes and degrees, but it cannot be reduced to that. So here, modes of thinking conveys this general idea of something that cannot be reduced to a strict system of given structure. Modality will allow for the inter-influence that I want to emphasize. The first mode of thinking will be that of verifiability. This is what mathematicians do when they produce something, say a proposition, a general term I will use here, a proposition that others can check. Checking here means that the proposition has been produced in conformity to a rule. I will come back to this in detail in a moment. The other claim is that there is a second mode of thinking, which is a progressive mode, and in which things are more tangled and complex, in fact. So the aim of this work is to clarify those two modes of thinking, explore where this leads us, and draw all the philosophical consequences of starting from such a position. So now I'm going to go into details and try to give a clear grasp on this. So first, the technical tool, a purposeless machine. The idea of such a machine is a way to take the verb to think in a neutral and theoretical position way. The idea I would like to start with is mathematical thinking, and I want to take it in the sense that thinking is what a machine without a purpose does. A machine that must be thought of without fixing or even without knowing what it is supposed to produce or manipulate. It's not a closed machine operating in self-contained isolation. Rather, it operates as an organ without function, an organ ready to receive whatever it can accommodate, however unexpected. So the capacity to think is a capacity to produce and manipulate, a machinic capacity without the need, when imagining this capacity, to conceive from the outset what is going to be produced or manipulated. And this idea of a machine is essential because, in fact, we have no idea at all about what is going to be manipulated or produced. Mathematical objects, realities, abstractions, ideas, either with a small I or big I, depends on what you are thinking of. We all know that they are problematic, in fact, and lead to a diversity of stances in philosophy, which are not very dangerous, of course, but which fail to fully convince anyone, either philosophers or mathematicians. Just a remark now. It might look like a black box approach, but that is not at all the case, in fact, here. On the contrary, I want to use this idea of a purposeless machine as an abstract, theoretical, fully clear, tractable starting point from which I want to extend the theory of thought, first adapted to mathematics. What gets in or out is not clear right now. At least it's not what I want to focus on initially, which is quite different from some classical approaches where we first concentrate on what is given to us, what we can perceive, and then we elaborate on what we can do with it and why we can do with it. Brings us back to Kant and that kind of thing here. Mathematical thinking will, therefore, be completely disengaged from the notion of the object of thought. Disengaged doesn't mean that there is no object. I will return and to a redefined notion of object shortly. For now, the key point is that mathematical thinking should not be tied to an a priori given object. Now, when you get rid of object of any kind, the very notion of thinking is not very easy to grasp when you view it as the activity of a purposeless machine. You might feel right now it emerges in a kind of mist as an idea whose content is still to be properly defined, and you're totally right with that way. So I will now explain what thinking means or how this purposeless machine functions when it is acting in mathematics. That is, when it acts in the act of mathematical thinking, or as I prefer to say, when we exert our force of thinking in mathematics. Let me say a few words about exerting our force of thinking in mathematics, because I want to start with something about which we have no doubts at all. Once again, the situation I want to capture here with these words is exactly what we mean when we set our mind to do mathematics, not to bring something to do mathematics, okay? It's a specific intellectual activity, a very common one. And of course, I'm not suggesting that this is the only way to exert our force of thinking, but at the very least, the fact that we can all do it seems to me something we can agree on. There might be some exceptions here, but I won't give names. We're online. I think we can do mathematics, okay? More seriously, I want to say that there are many ways of doing mathematics, and maybe a theory of mathematical thinking cannot be fully isolated from a general theory of thought. Things are not totally compartmentalized, and my theory will also allow for that. So now let's take a closer look at what thinking actually means in this context. I've promised a small example. So there will be an example. So say, before I show the example, we are at school, okay? Not somewhere else on the planet or something, or not at the university or in a laboratory where mathematicians work. And I show you 4 propositions, and one only should be correct when you are at school. Which one? So you go through the different proposition, and you should obviously say the second proposition is the correct one in the context of a school. So anyone here was able to check which sentence was conformed to the rule, check was true, and the rule being here implicitly given by the fact that you are at school. But when you have actually done the verification, you have treated 2 here in a specific way. You have forgotten, what is important to me, was on one of the slides. So you have forgotten the time of the process of the verification that 2 was, say, even. But it could be a real number. It could be a complex number, depending on your background in math. It could be an ideal in a ring. It really depends. Of course, some of you might have thought for a second that the 4th proposition here was also true in a different one context, and maybe the other ones too. But in a school, you know the rule. And obviously, you're not working in F3, the field with 3 elements. So you know the second one is the right one to pick. If there is a starting point which doesn't embark too much from the outset, it must be compatible with this kind of example, I think. So I'm now going to use what you felt from manipulating this example to give you some flesh to more abstract and general idea. Small examples like that are dangerous for two reasons, in fact. The first one, because they might not represent the diversity of situation that we can encounter in mathematics, might give a somewhat partial and false idea of the full picture. And secondly, because they put the philosopher at risk by allowing anyone in the room to get into the debate. I prefer general philosophy, so I totally assume the second type of risk here, and we'll have discussions about the twos and the ones and the three. And for the first type of risk, well, about a restricted view, I think it is working well, since it gives a clear view, even in a simple case, of what I want to start with, in fact. So now the process of verification and invariance. We now enter the core ideas. One of the activities of the mathematicians consists in creating propositions that are verifiable, meaning they should conform to a certain rule, and then verifying that conformity by a proposition, or maybe I will say a statement sometimes. I mean a product of mathematical thought, which can be expressed in various forms: in writing, on the blackboard, on the gray board, in publication, spoken, or even internalized. The form doesn't matter here. What does matter is that the verification process can take different forms: peer review, self-verification, or the spontaneous assurance that one is thinking according to a well-established rule, in which case the rule itself conforms the statement, so to speak. But this is not the only form of intellectual activity that mathematicians engage in. They also think beyond the strict observance of the rule, which we'll explore a bit later, and they even make mistakes. Yes. Even mathematicians make mistakes. But in a suitable context, 2 + 1 = 3, and I have no doubt that I've thought of this equality in accordance with the rule that I've followed. But also think of propositions that are not mathematical propositions in the sense of a theorem, if 2 + 1 is a theorem. For example, the sentence, let's consider a continuous operator on a Hilbert space. Stop. This is also confirmed by rule, and any mathematicians will say it's correctly formed. So let's dig a bit deeper into this. When I say, take A and B in the vector space E and consider their sum A + B. This makes sense. It makes sense because it's conformed by a rule dictated by the axiom of vector space where you have an addition. But when I say consider the product A times B in this context, then something went wrong or something is missing. It is very important that the process of verification is something mathematicians can share among peers, but also share across time. If you read the lecture by Weierstrass on analytic functions written in German in the middle of the 19th century, you might think the rules have changed and that you no longer consider the same problem exactly as Weierstrass did. However, it is possible to adopt his rules and follow his reasoning, adhering to the exactness of what he says, or sometimes the ambiguity. A proposition written a century ago is not true forever. It's true as long as you can adopt the rules it was developed with. Of course, something might be false within the domain of applicability of the rule, or the rules themselves could be incoherent or simply inapplicable as rules. So now we touch on two things here. There must be first a principle of invariance, which we call IP, invariance principle, to explain the capacity of an external observer to grasp the rule and verify a proposition. And secondly, the rules must evolve in order to allow for the constitution of a domain of knowledge over time, to explain mathematics as a domain and to provide a clear idea of a form of permanence, a form of unity that has often been acknowledged. Maybe I can be a bit more specific about this. Looking at this usual picture here, what I don't want to say is that what is meant in Pythagoras time has nothing to do with what is meant in Hilbert space. I simply say that the verification process is not the same. More than that, I think that I have a theoretical explanation for the fact that there is a connection between the two, which can be read in the way mathematicians change the rules and change the game over time. I want to deal with the historicity of mathematics here, since it will take a long time, but I will present the mechanisms that will make the evolution of the rules and the progression of mathematics possible here. So now we have this inference principle attached to the possibility of verification. But let's go back to our simple proposition 2 + 1 is 3. I want to say something more about this simple thing. I want to say that 2 in 2 + 1 = 3, you have this in mind, is not defined as a being by the scope of the rule, nor by its application in the process of verification. There is indeed something about 2 that exceeds what I need to know in order to check what it has been, that it has been manipulated according to the rule. And conversely, and this idea is in some sense, in some way dual to the previous one, the scope of the rule, the full domain where it acts, cannot be defined by the various uses of the rule in the verification process. This is very important. This is not enough to define where the rule acts, just to look at where it acts in the verification process. Right away, we are facing some hard questions. What is 2? What is an object? What is the legal domain of a rule? And so on and so forth. What is clear to me is that there is a first mode of thinking, which is the one at work when mathematicians produce statements according to rule and validate these statements. This process of forming statements according to rule and verifying them require a certain objectivity, of course, but I don't want to address this question of the object right now, as we need more before we can do so without ambiguity, in fact. It will depend on the invariance principle, this one, but also on something else I want to introduce first. So here, just keeping in mind that in this first mode of thinking, the rule is used in the verification process in a reliable and shareable is important, it's into the advanced thing, shareable way. We shall see that the rule also acts outside its field or the field of verificability, outside what I've called its legal domain. Okay. So now, I don't know the English for hors champ, so I put the French here, but I think you understand what it means, and the forgetting function, because I want to deal with what is under the surface now. Think of the situation we have just considered in my small example again. We were able to think of 2 in a way that allowed us to verify the correctness of the second proposition, while being able to say much more about 2 than what we used for the verification task. There are, in fact, 2 things here. First, I pretend that there is in 2 more than what we needed in order to check that the rule was well used. And beyond that, I said that rules also act beyond their legal domain, in a world that only a progressive mode of thinking can give access to. Maybe think of this at the surface of a viscous liquid on which you can draw shapes without doubting that you are acting at a much deeper level. To draw a circle, or maybe acknowledge that you actually drew a circle on the surface, you forget that something is happening deeper below the surface. And there are rules determining that it is actually a circle you have drawn. To be able to verify the application of a rule, there must be a forgetting function that allows us to take 2 as what is strictly necessary for the verification process. If you are bored with the 2's and the integers, you might think of anything you have in mind more substantial and mathematically interesting. But I think the integers are interesting in this case. So I chose the word forget because it's very important. It took me a long time to take this word, because when you forget something, you know it is still there. It is just a question of access to it. More than that, you may forget something on purpose in order to follow a rule. When you are in a kitchen and you follow the order, put this mug away in the cupboard, you definitely know what to do. And you forget something that you also know, the color of the mug, that is made of atoms, etc., etc. You follow the rule. But let's say a bit more about this forgetting function in our case. The result of the forgetting function, I think, and this is very important, is a semi-detachment that I want to contrast with abstraction, which acts as a total detachment. When you move a mug, you don't think of the atoms, but they are so close, so easy to consider, that this forgetting function is not in a total isolation for verification and following the rule. Concerning abstraction, the contrast is quite revealing. When you think of a circle as an abstraction from a collection of encountered roundish objects or forms, then the circle as an abstract entity has been analyzed in philosophy as fully detached from the thinking subject or from any background. This is a common view of mathematics, which underpins many philosophical conceptions. And my approach wants to depart from this view, in fact. The semi-detachment I'm introducing through this forgetting function is a partial but sufficiently strong detachment from the thinking subject and from any background. So just a remark here, I'm not entirely happy with the word function here, because it's a term we use in math, so you have to understand what I mean. And I guess the context is clear enough to not to mix this kind of function with something like function in math. The word functor is also used in math. They have picked all the words so around funct something. So okay. So I think we have now a sufficient theoretical position to grasp what objects can be in this theory of thought. They can be defined thanks to the conjunction of two things: the invariance principle and forgetting function. They allow us to do the verification thanks to those two characteristics. So I think, no, well, I don't give a full definition. I just say those two are very important to get the idea of an object. I say a bit more now. This is the total rethinking of what an object is here. So maybe a bit of analysis of this object. The ob here bears, I take the mark of the semi-detachment, while the Jaeck is linked to the result process of the forgetting function, both supporting an invariance possibility. I've said before, it has to be contrasted with the usual analysis of the object as a full detachment from the subject and from any background. You might think for a second it's an ob-leviate to best render this contrast. So when I speak of an object, please think it as these two things and the result of something like linked to the invariance principle and the forgetting function. So concretely, what are objects in mathematics and what mathematicians manipulate according to predetermined rules? Maybe I have to specify those rules in what follows. They are not always presented in terms of formal logic. Depending on the field of mathematics, you'll find elements that are not governed by the same logical laws, nor by a single uniform axiomatization, and rules that depend themselves in other forms will be at play. However, locally, in a given practice, in a given field, in a given historical time, in a given mathematical ethos, we could say, mathematicians know what enables them to form statements that conform to the rule, and they manipulate what I have called objects according to the rules. So objects, as I now understand them, include, of course, sets, categories, elements in arithmetics, functions and function space in analysis, geometric objects, etc., etc. But also what mathematicians call structures, including groups, spaces, topology, and so on. A multitude of elements which have in common that they can be manipulated according to rules, to which we are supposed to be able to refer to validate the way in which they are or have been manipulated. Real numbers, vector in Euclidean space, function in L2 spaces are objects only insofar as they are manipulated according to the axioms of a vector space or topological space, or both, for example. Looking at this very partial list here, it becomes clear that there is a lot more than behind these words than their objectual quality. Each of them can both serve to verify a theorem and also plunge us into another form of thinking, which I'll come to soon. So now just keep in mind that objects are linked to a first mode of thinking, verification, that a rule has been followed, and depend on the form of inference and on the result of a forgetting function. Maybe a quick remark. There is a first mode of thinking which is that of verifiability, and I don't want to say that mathematical objects are everything that fall under the verification process. When I say let x be an integer, there is an objectivity of each word allowing the verification that the sentence conforms to a rule. And this rule is mathematics too. But here, when I say let x be an integer, x as an integer is the mathematical object. So now, to get a clear grasp on the two modes of thinking, we need to say a bit more about the rules and their applicability. First, we need to say what these rules are that mathematicians use, how they can know the rule, and what those rules are supposed to govern. And secondly, we need to determine how the rule acts outside the scope of the pure law it determines. In other words, and by way of complementarity, what does the rule actually qualify as an object, how it does so, and what lies beneath the surface of it. But first, let me say two important things about our first mode of thinking and its close relationship to the rule. First, mathematicians in their way of thinking and manipulating objects are also aiming at an indeterminate horizon where new, unknown objects can enter the scene. The objects and the rule are set in the same movement and they evolve over time. Secondly, of course, the rule is not totally linked with the game it enables to play. In a given theory, in a domain given by rules, the mathematician is faced with a game that can be played according to the rule. Mathematicians are players, and exploring a game with rules whose rules have been given to them is one of their first activities. And there I would like that the goal is not to explore all the possibilities offered by the game, but to develop a playing skill, to understand its strategies, to understand its scope, without reviewing all the particular games that could be played. I use the English game, but in French we have two words, in fact. We have le jeu et la partie, which are two different things. Maybe you can grasp those difference between the two words jeu, partie, which are quite different. A full game we play once is the partie, and the jeu is the abstract thing of all the possibilities, in fact, and given by the rules. But more than that, mathematicians also think of new games, change the rules, and evaluate if the new ones lead to a nice game. So now it's time to say a bit more about the scope of the rule. In mathematics, the rules for manipulating objects and for the general verification process are forged at the same time as the new objects that will have to be manipulated according to these rules, thanks to something that is not foreign to them, in a domain that falls under the rule in spite of it, if you want. At the same time as I delimit the notion of objects in mathematical practice, I need to specify the rules that come with it. There are of two types, in fact. The first are the rules of logic, whose long history show that they are constantly evolving, not only in order to find solid foundation for the manipulation of objects, but also to adapt as best as we can to the needs to manipulate new candidates for the status of objects. But there are other rules too. Group structure, for example, requires that groups elements be manipulated according to the laws of the operation that define the group. Any violation of these rules would be unacceptable. Here again, numerous works in the history of mathematics show that these types of structures and the rules derived from them, from the axioms, are created in connection with the objects one wishes to admit to the mathematical scene. Objects whose existence is sometimes defined, a solution to an equation, a fixed point, or something else. An existence that mathematicians will seek to establish according to rules fixed at the same time as the idea of the new being is grasped. I give an example. When in 1919, Banach defines the notion of a complete norm vector space and then establishes some important results in the game. The rules are both those of logic and those instituted by the axioms of the space, themselves compatible with a logical framework that Banach does not recall. In this case, as it is often the case, the game, not yet played, not fully played, it will never be fully played. The game and the rules are forged in the same movement. More precisely, complete norm vector spaces were introduced by Banach to provide a general framework for results that seemed to him to be based on common strategies. He thus worked from a number of functional equations on various spaces from which he derived general rules, deduced from those used precisely to establish results in each particular case. In the same way, a few years later, when working on functionals and their extension, Banach chose the rules he felt were best for obtaining extension results that would enable him to advance his theory. Okay? For example, he admits the axiom of choice without discussion, and this, in fact, complements the axiom of Banach space, of a Banach space. It's not first I take those axioms and then I beat a Banach space. He has Banach space. At some point, he needs the axiom of choice. He takes the axiom of choice in the game. These rules are not the only possible choices, and sometimes they aren't even necessary. For example, the axiom of choice is not useful everywhere, and a number of theorems established by Banach can be proved without it. But he works under the condition where you have the axiom of choice. But for Banach, the game he adopts is one in which the functional can be extended and the existence of new objects, in this case, extended functionals, need to be deduced from the rules defining a complete norm vector space. He therefore has the ability to aim for an object horizon that prepares the ground for objects that don't yet exist. In the context I just mentioned, Banach wanted an extension of functionals to exist before it could give the exact framework that would allow it to actually exist. What I call a game above is precisely the possibility of exploration on the side of the objects and the exploration subject to rules for the same time as the objects. Maybe let's take another example to illustrate the construction of the rule and the co-construction of the rule and the game. Let's suppose that the concept of vector space and basis have been established subject to both the laws of logic, say in Zermelo-Fraenkel set theory with the axiom of foundation, for example, and the laws given by the structure of a vector space. So it's a basic example here. Accepting the existence of a basis for every vector space is in ZF set theory. with the foundation action, equivalent to admitting the action of choice. So if we want to play a game where we have a basis in every vector space, which is very often the case. If you have no basis, it's very hard to work and to say it's interesting to be in a vector space if you have no basis at all. So we need something like the action of choice, the rule, which has been shaped precisely to make this kind of game possible, and we find ourselves in ZFC. This idea of a co-construction rule and game makes it possible to explore the full diversity, in fact, of situations encountered in mathematics, and to think of the notion of objects in a way that is not limited to by an autonomy that they don't have. If we return, and maybe I end with this thing, instead of giving more examples and getting further, if we return a moment to the extension theorem for functional, so the theorem is given space, and there is a bigger space. You have a functional, it's a function. So you have a function defined on the first space, and you want to extend it. So it works on a small space, but also, as it was working before, and also on a bigger space. And without increasing the size of the function in a sense. Extension results. So if we return for a moment to the extension theorem on functionals, which is called the Hahn-Banach theorem, this has been demonstrated historically by both mathematicians, Hahn and Banach, in a non-concerted manner, using, still in Journal of Frankel axiomatic theory, Zorn lemma equivalent to the action of choice. But in fact, the ultrafilter theorem, which is equivalent to the prime ideal theorem in a Boolean algebra, this equivalence is probable in ZF without the action of choice, in fact. This makes it possible to prove the Hahn-Banach theorem. But conversely, we know from David Pincus in '72, who worked on the Hahn-Banach theorem, we know that the Hahn-Banach theorem is not sufficient to prove the prime ideal theorem in ZF. Thus, the Hahn-Banach theorem, which is the result proved by Hahn and Banach, is not equivalent to the action of choice in ZF. We see here how the rule and the game are intimately linked and how the notion of object is deeply associated with them. The existence of an extended functional represents, depending on the case, the rule, the game, or the desired object in theory. That's here. Thank you.
We take a 3-minute break and we have plenty of time for questions.